Hold on. Welcome to this wonderful adventure of the New York City Category Theory Seminar. Today we have James Austin Myer, okay, and he's talking about the Bloch material, a simplicial set for every variety. Anyways, take it away. Take it away.
Okay. So the first thing I want to explain is why you would even be sort of interested in doing such a thing. You might say, well, that's interesting on its own, but the motivation is sort of as follows. So, we don't know as a community, we don't know whether every variety admits a resolution of its singularities, which I can sort of elaborate on a little bit. I'm not assuming that people know what that means. We know this in certain cases, but let me just say what that means. So a resolution of the singularities of a variety is, so you have some variety. I'm going to assume that people kind of know what a variety means. If you don't quite know what it means, think of something cut out by polynomial equations or something over some field, which could potentially have positive characteristic. A resolution, usually is regarded as just like another variety and a morphism from your variety, or a morphism from this one to that one, such that this variety is what's called regular. Okay. This morphism has to be sort of particular. It has to be what's called proper and birational. So I can elaborate on what these things mean. Proper, for us, you can kind of think of proper as being like, trying to think to what extent I should really get into that. Let me ignore that for now. So birational just means isomorphic on an open subset. Isomorphic on in this situation, an open subset is a risky topology, right? I'm using the risky topology. And proper, I mean, we know proper from maybe geometry and stuff, right? So that's like, the preimage of a compact set is compact. That's kind of essentially what this means. So in the sort of usual setting, proper means what you think. If that's okay for me to say. In this sort of like algebraic setting where you actually have some variety over a finite field or something, it means what's called like universally closed, which is to say that it's a closed morphism that is closed after all base changes. But this is like not really giving an impression of what this means. I mean, the idea is you should think of like you have some quote smooth variety that happens to have a map down to the one that you're trying to resolve the singularities of, and that map is that morphism in particular is like essentially like a projection. That's actually somewhat related to some of the problems. Whether this is a projection is something that I'm actually a little bit curious about, and I haven't really been able to completely sort of handle that. It seems like it should always be, but it's not always. Maybe I don't know. Anyway, and then regular is just a kind of fancy word to say. It's a fancy way to say it is like a manifold. Well,
But it doesn't have singularities.
Yeah, it doesn't.
Otherwise, you wouldn't be resolving them.
Yeah, exactly. So,
Can I ask where would the trouble be? In other words, for this thing, I could see two resolutions. So why?
so like this thing.
And then you can. Yeah, sorry. So, I mean, where would there be a problem? Why is this such a hard thing?
But why is it such a difficult problem to solve?
Right. In other words,
Why?
take anything and, it seems like you can disconnect it in many ways.
Well, but remember, they have,
Ah.
these have, remember, yeah, there has to be algebraic, so you have to do with using algebraic equations. You can't just do it topologically.
Well, also, this is just a curve.
Right, so,
Yeah, so for a curve, I agree. This is relatively straightforward and it follows by doing what are called, these are called blowups.
Yeah.
and so is there some theorem that for any curve, then there are resolutions?
There's an algorithm.
Yeah, and up to dimension,
Yeah, it's not explained. Yes,
Okay.
curves. All good. We know what to do with curves regardless of the base field or anything. Like, I'm not even getting into that yet, but you can imagine you could work over like F2 or something and then weird, right? Surfaces. Sort of however generally you could imagine. Good.
easy.
Okay, threefolds. Almost, I think, right? I think we just barely know this. Okay, fourfolds. This is unknown unless the characteristic of the base field like the field where the coordinates live in some sense is 0. Right, and that's old work of like Hironaka.
Yeah.
Like 1963-ish. Right. And then we don't know. And it's curious that we don't know this, but it's like, you think we might, like you said, like it's like why should it not be that if you perform, a bunch of these blowups, you should eventually get the answer, right? And yeah, so it's startling that we don't know this in some sense.
It's unknown in characteristic 0 for all above too.
Oh, excuse me. It's known so if characteristic of the field is 0, we know what to do. Everything's done. Excuse me. Characteristic 0 in general. Field. It would, to be clear.
Especially complex numbers.
If you're confused or something, like complex. For all dimensions.
Right, so the point is, yeah, complex numbers, topology, it's what you said, but the problem is, you try to do, like you said, over some field with a prime, then how do you, then what?
The problem is that like derivatives don't behave well.
Yeah.
When you have things like 2 = 0, right? You can imagine, of course, this is already an issue, but you can imagine like if you have an equation like y² = x cubed, and then you differentiate it, you have all sorts of issues now. So the singular locus can be sort of much worse than before in some sense. Right?
If you have to do multiple blowups, how do you know that you don't run afoul of your characteristic?
Exactly. Yeah. So anyway, so this is the idea. So does everybody feel like I understand the problem that's desired to be solved?
Over C is regular equal to smooth.
Yes. So excuse me. I say regular just because I'm kind of traumatized by situations where that's not the case. But yeah, I mean, smooth and regular are the same for the purposes of this talk. So that you can just assume you guys are the same. For our situation.
Yeah.
Yeah. If you wanted to say smooth, that's totally cool. Okay. Now, yeah, so what to do? Well, considering people haven't been able to figure this out for a long time, you might start to wonder if it's false. Okay, now I don't want to say that I think it's false. I just want to say that I don't know. And so I'm happy to know anything, I guess. So back in 2000.
Stating it's false means there's no algorithm that does it.
And it means, in fact, that there's no way at all, maybe.
Or they have a really nasty singularity you just can't resolve.
Where there's no way to find a proper and birational morphism thing. Yeah, maybe there's just some weird counterexample out there. Okay, so let's sort of think about the sort of characteristic 0 story for a moment. So back in 2004. Dennis Sullivan sort of suggested, it's kind of amazing actually, it's only like a sentence or two, in a memorial article for René Thom, a possible way, or well, just a way to learn more, I'll say, about this situation. By way of his obstructions, to the representability of a cycle and homology of the topology. By a manifold, which I will explain. So suppose you have space, and in that space you happen to have, let me call this by like P. Okay, so you have some space, and then you have some cycle and its homology. This is just a cartoon, but you know, think about this. So this is like, say, sigma H10 of P with coefficients in Z, let's say. Then you can ask, is there a manifold? So presumably outside of the space, which could be outside, a closed manifold. So closed meaning, you know, has a fundamental class and everything. So that there's also a continuous morphism to P with the property that when you push forward the fundamental class of M, the manifold, you get the cycle. So in other words, can you always regard this cycle as a manifold up to sort of homology, right? So that's a very similar question. Yeah, already on the surface, you can sort of see that, right? It's like, I want to replace this thing with something that's like a manifold. In particular, I should mention that a proper morphism has the property that the fundamental class of this will in fact push forward to the fundamental class of this. And you might say, well, how could that even make sense? Like, this is singular, so it doesn't have a fundamental class, maybe. So let me kind of elaborate on what I mean by that. So, for example, any complex variety I guess, however, singular, enjoys a fundamental class. Because essentially because, I mean, you can complain that I'm not really telling you the whole story. And excuse me, I don't really want to get into this right now, but if you want to ask me afterward, maybe I can try to get into it. It enjoys a fundamental class essentially because the singular locus is in codimension, complex codimension. Right. One. Yeah. Right. Or more, or something. So in some sense, the idea is that like you're going to be able to build an orientation class.
In the intersection homology?
No, in the singular.
In the singular.
Singular homology. Yeah. So you'll have a fundamental class, regardless of the singular locus. And so with that said, you can ask this question for the fundamental class of a complex, potentially singular variety.
And just to be clear, so in this problem, there's no more characteristic P, this is just
Oh,
ordinary
this
topology
is-
at this
yeah, I'm
point.
talking about complex varieties and analytic spaces associated with, like, in other words, like, you know, just think like, yeah, I have a thing cut out by polynomial equations over the complex numbers, and then we'll just have some coordinates.
Should the variety be like projective or something? It's like we're at finite things.
Oh, excuse me, yeah, any projective complex variety, right? Yeah, thank you, yeah. You know, or proper or whatever, you know, something with a closedness property. Okay.
Can you just restate this sentence here?
Of course.
So where you're not making a statement because you're saying we want to learn something about it. So presumably if there's a
Yeah, this is a question, excuse me. Does there exist such an F? Always.
right, so you have a nice cycle.
Yep.
Okay, and you want to know, does that cycle come from a nice manifold type thing?
Manifold, yeah. So in other words, can I find a manifold whose fundamental class, which is a cycle, is
So this is like classic obstruction theory.
exactly, yeah, exactly. So you can imagine why Dennis would be
C.T. Wall from the 1950s.
yeah, exactly, very old stuff with this, yeah. And then René Thom has this sort of, you know, famous attack on this problem, which I'll say a few words about. Okay, so now we're all on the same page that complex projective variety, say, has a fundamental class, and so we can ask this question: is there in fact a?
And by the way, you have panel number 4.
Yeah, he moved it.
Oh, fantastic. Okay, thank you. Yeah. So now, let's say you have a projective variety, so it lives in some projective space or something, right? I mean, technically, I don't really need an ambient space to say this, but whatever. And then you have some X, right? So this is just a cartoon for the sake of having a picture, right? So this thing has some class, which I'll call a class of X in some sense. And then you can ask this question, but what you realize pretty quickly is if you have a resolution, right? So if we have this resolution that I drew on the board before, right, then it is in fact true that if I take the fundamental class of the resolution, a proper morphism, that's sort of the point of properness in the sort of classical thing. Sorry, you don't have to look at this. Yeah.
Oh,
It'll push forward to the class of X by F. Okay. So in other words, like I'll sort of summarize all of what I just said by saying a resolution of the singularities of a complex variety, say projective, whatever, affords us a solution to, well, excuse me, I didn't say this problem is attributed to, which is a bit of a shame. So this is Norman Steenrod. Norman Steenrod problem, which is sort of funnily not written by Steenrod. It's actually written up by Eilenberg. One of the problems that he lists in some lists of problems for topology. I think this is like, he writes this as like problem 21, I think.
okay. So his version of Hilbert problems or something like that.
Exactly. Yeah, it's like some.
So Dennis's thing is to relate it to
Oh, I'm gonna say here. Yeah, I'm gonna say.
in other words, you're talking classic algebraic topology.
Super old. Yeah.
I mean, I thought it was embarrassing to say CTC Wall, but you're going back to Sammy Eilenberg.
Oh yeah, no, this is old stuff. Yeah, super
Okay.
old stuff. Yeah, this is 1947 or so. 1947. The question is sort of raised in some sense, and then René Thom takes like until approximately 1953. 1953 is when he writes this paper which has a name in French, which I will not try to pronounce. It's like Bob case, something varieties differentiability, right? Like on properties of differential manifolds or something. And yes, but I'll say here quickly what this is, and then I'll summarize that also. So a resolution of the singularities of a complex projective variety affords us a solution to what we'll call Steenrod's problem. Okay. For the fundamental class, that variety.
Yeah.
So they were talking classical algebraic topology, and you want to talk geometry.
Yeah, we wanna see how this relates to algebraic geometry. I'll explain that also.
Okay, so the impression I guess here is, we know what to do if we start with how to resolve singularities for good old complex varieties. So there's two ways of generalizing. One, you say, well, replace the complex with some characteristic P. The other way is this way of generalizing it, or to a problem in topology with manifolds.
Well, it's like you have this problem about manifolds, or about cycles and manifolds. And then it's only much later, like I'm saying, like 2004. I mean, probably Dennis was thinking about this before then. And maybe other people, that's what he sort of suggests, which I can say a word about. That like maybe well, the first observation is in particular a resolution of singularities of a complex projective variety affords us a solution to Steenrod's problem, which is to say, if you're familiar, or like people that do know about this, Thom's obstructions vanish. There are obstructions to solving this problem in general, which are sort of Steenrod operations, right? Thom's Steenrod operation obstructions to Steenrod's problem must vanish then for the fundamental class of a complex variety. That's an observation. I mean, by Dennis, as far as I understand, maybe before, I don't know. I mean, but certainly by Dennis in this article, right? Which is, super late, 2004. Right? Otherwise, I don't know of anybody really thinking about this. So, in between, I could be wrong. I don't know. I mean, I'd be happy to be shown that that's not true. But yeah, I mean, Dennis has mentioned to me that he sort of thinks that like maybe, René Thom was aware of this problem, right? Resolutions of singularities. I mean, he was working on algebraic geometry just the same. Serre and all these people, they were thinking about this. And there's like Dennis has kind of like, loosely suggested that like maybe actually Thom was trying to build a counterexample. And then Serre even. And then that was corroborated in an email where Serre said, what's that? What is the Steenrod problem? Oh yeah, of course. Yeah. So the Steenrod problem is, so you have a cycle in the topological space. So in other words, you have something in its singular homology, and you ask, is there a manifold, a closed manifold? So in other words, a manifold with a fundamental class, and a continuous function from that manifold into your space, so that the push forward of the fundamental class of the manifold is equal to the cycle that you have. Okay? So in other words, can you always regard your cycle as, yeah, of course, yeah, that's super important, yeah, to understand. So can you always regard a cycle as being represented by a manifold, and in particular, if you have a complex variety, however singular, it has a fundamental class about which you can ask this problem. Can you solve Steenrod's problem? And the answer, thanks to resolutions, singularities, is yes. Right? These must vanish. Excuse me, I didn't finish the sentence. By an arc. Just by this kind of huge, right? Like just like sick this massive proof on this thing, and it has to just by implication has to be true. But you could ask, well, why do they vanish? Right? You can get into the topology of it. And so I know there's some work by like Chow, who was here as a postdoc for a little bit, where he sort of investigates what the algebraicity does. actually, in some sense, like without using Hiranakas. Okay, so what is this obstruction theory? Like, how does this kind of work? So I want to say a few words about that, because it's related to why you would want to make this simplicial set. Do people have questions though, before I start talking about that?
Hey, so I just trying to put it in context.
Of course.
There's a problem about all varieties.
Yes.
Right.
And Dennis remembers that there's an old problem in topology.
Mhm.
Also, you want to get a manifold type thing
Yes.
to do it, but he's just dealing with one cycle. And so Dennis's idea or your idea is that maybe Dennis's idea. Dennis's idea is that maybe if you can just do it for lots of cycles, I assume, then you can somehow build up an answer for any variety.
Or if you couldn't do it for a cycle, that might tell you why it can't work.
I'm gonna say the opposite thing. Yeah, so imagine I found a variety for which we could not solve Steenrod's problem. Then I would know that there could not have been a resolution, because if there were a resolution, I would have been able to solve the problem. Now, in the complex setting,
Mhm.
again, we can solve the problem.
Right, that says characteristic zero.
Exactly,
Yeah.
characteristic zero. So then you say, but then what about positive characteristic? Oh, but then
What do you mean?
what does that mean, right?
Yeah.
It's like, what are you doing? This is all like topology, right? So then how do you do this? Right, so, okay, so, yeah, there are other questions about. Okay.
Oh, so if you only believed in complex numbers or real numbers or other nice things like characteristic zeros, then this is all trivially true.
You're very happy.
Right.
Well, it's might not trivial, but it was solved a long time ago.
Right.
Yeah.
Okay, fine.
Probably the universe is finite. This is joking.
Okay, so you're now going to tell us how
Okay,
to.
now typical Jamie rant about the.
Sorry, go on. One second. You want one. Don't move.
I think you need to start the video. So
This meeting
You
is
need to
being.
Yeah, you can kind of recalibrate.
No, not there. No, it's not connected here. Don't move, ladies and gentlemen. We're right here. Maybe I could remove spotlight. Okay. Is that an integrated webcam?
I think you just need to click on it so that the red thing.
Well, now it's coming from here. You can.
Yeah.
Oh,
Okay,
perfect.
but now you need to switch to
Oh,
red.
They're both the
You're looking at the wrong. Don't look at me. I don't exist.
Yeah, that one. There.
Okay, we're back to normal. Sorry. Okay.
So, yeah, resolutions. Positive characteristic. Can you develop an obstruction theory analogous to Thom's sort of usual topological setting, so that at the very least you could define the obstructions, and then who knows? I mean, maybe you compute them and you find that they're all zero. In other words, there's no problem, but you never know. I mean, find that there is something. It's like, there you go, you're going to counter something, right? But I'm not saying that, like, I don't know. I'm just trying to build the thing. Somebody can maybe come along.
Right, one step at a time. First, you have to figure out what it even means. Then you can.
What does it even mean? That's the first part.
Yeah.
Okay. So with that said, it's like, let's review maybe like a classical obstruction. What do you actually do, right? So you start off by saying, well, you have this variety. So I'm going to make a diagram here. You can see this, right? Yeah. Okay. Good. So I'm going to make a big diagram over here. So this is probably the most category theory thing so far. So you have a variety X, and I can regard the variety as being projective. This is sort of a technical lemma in this area. So I can imagine that this thing lives in a projective space if I want, up to some birational equivalence or something. So let's assume that. And then I can perform a blow up, which is like that picture I just drew. I'm going to abbreviate that by blow up. I mean, technically what's going on here is you have I'm sorry, I keep doing that.
I'm just sliding over.
Okay. Just moving around. And so you have, and really this curve is inside of a projective space, right? It's in P2, right? Gonna put things into perspective. And then what you're really doing here is it's an A2, but it's inside of P2. Like the affine space, but then you can draw it like that. Then you do a blow up of that space, and you get this blown up surface, right? Which I'm, for the sake of time, I'm not going to try to draw in any reasonable level of accuracy. And that blown up surface, I'm calling B, right? For blow up. Okay. So in other words, this resolution is, quote, embedded. It's happening inside of an embedded, right?
Putting it in context.
Right. So intuitively, in that example, you're in two dimensions out enough. If you add a dimension, then I take the things they cross and lift one above the other. So
Exactly.
they don't cross anymore. It's no more singular.
Exactly. And so like if you've never seen resolutions of singularities before, that's like the quintessential idea. And
Yeah.
in fact, you can ask the question a little bit more like meticulously, like you can say, in fact, can we always do this in such a way that we're doing blow-ups? Like so that the proper morphism is actually just a composition,
Right.
simple sort of nice blow-ups, right?
Mhm.
Because it should be, that's what we expect. And then this morphism that we're asking for, this like resolution morphism, is really just the sort of restrictions in sense of this map. And then from there, I might even want a little bit more. A little bit this way. Okay. Well, then from there, still a little bit unsure about this, but let me just say it anyway, and then we'll see how this goes. I mean, certainly I can put both of these into a sufficiently large mutual projective space. So now n is the same, right? These are the same projective space. And so this is a bit of a conjecture, I guess. I don't know what to call this. It's a little frustrating to me that I haven't been able to sort of verify this, but maybe just well, you always have a projection from Pn to like capital N to little n. That projection is not everywhere defined, right? It's a rational morphism, it's a rational map. And then you might be able, you could restrict it, if I call this by Raj or something. I could restrict it to M. And when I do that, I should get, I would like for this map to be the restriction of that projection to M. See, this is certainly true in that picture, but I haven't been able to sort of verify that this is always true for every resolution, that there exists a sort of realizing or witnessing projection. But maybe for now, let's just kind of take this.
Just to explain, why is that not always defined from capital N to small n?
Oh, okay, so here's an example.
Because usually, a larger space can always be projected to a small space.
Yeah, here's take
What's
P2,
that map?
take P2, right? X, Y, Z. Venus coordinates. And then we'll go to P1. Well, excuse me, let me do this. And we'll do it by way of forgetting a coordinate. Okay. That turns out to be a projection, right? In a sort of conventional sense, yes.
But X and Y back might both be zero.
Exactly. But what if X and Y are 0, for example?
Yeah.
Right. Then we'll end up at
Oops.
0, 0. Right, and then
Oops.
not defined. Yeah. So there's some point from which we're not going to be able to define this thing. In general, there's some linear subspace, right, that causes an issue. So with that, this is like kind of fancy. It's like kind of ridiculous. It's like the point is X is in some projective space. You do a blow up, and then M is like the restriction of that, pullback of that. From there, you say, well, why would you do this? Like, what's the point of this? Well, there's a normal bundle now.
Oh, yeah.
See, M is regular or like a manifold quote. It turns out like regardless of base field or whatever, I mean, I can still talk about the normal bundle. It's still a thing. You know, you do it in terms of like sheaves or something. You can maybe believe this. If you're curious, you can ask me and I'll try to elaborate.
So
For now,
you have two embeddings, M into B and M into PN. For which embedding is the
yeah, that's a good question. I think what I want is N in P. Yeah, so I'm going to be thinking of the normal bundle. Yeah, in fact, let me denote that. It's a little. Right, I'll do this. Okay. So the normal bundle of that embedding, right? And then from there, with that normal bundle, I can build something called the embedding bundle. So this is really like, I don't know, I just want to call it by E, excuse me. But it's the embedding bundle. Now, what is the embedding bundle? Well, it's a bundle over M, right? It's a fiber bundle over M. And let's think about what the fiber over a particular point would be. So you have M. The fiber is all of the, well, over M, in the normal bundle, you have a vector space, right? There's some vector space, which I'll call by, yeah, I have to just call by V, but that's fine. And the embedding bundle takes a point M and it sends it to where what's lying over it is all of the embeddings, like linear embeddings of V into some affine space, which I am welcome to choose the size of or the dimension of. So I don't want to use N, I'll use like maybe capital D or something.
Wait, who's V? Does a normal space, a tangent space to M or some other space?
So M has a normal bundle.
Yep.
And so for each point of M,
Mhm.
do I have a vector space lying over
Right, but which vector space is that? Is that the normal directions or all?
the normal?
They are the normal
Yeah,
directions.
the
Okay,
normal.
okay.
Yeah, the vector space of vectors, yeah, vectors normal or like orthogonal quote to the tangent space.
Okay, that's what
Yeah, yeah.
Good.
Um,
That's for you.
Yeah, so this is V. So for each
Mhm.
M, we have such a V. And then we can take that V and we can form a set a priori of just all linear embeddings of V into an affine space of a dimension that we have parameter for.
Mhm.
We can make it really big. You know, so is the dimension D of the affine space inside the embedding fixed? It's allowed to vary, and that's crucial. It's super crucial. I want it to vary. It's a variable. Okay, so this is a parameter that we have access to. In particular, I can make this D, quote, infinite. That's interesting. Okay. So this is some fiber bundle, right? It's not a vector bundle anymore. It's a fiber bundle. This set actually turns out to be an algebraic variety.
if M is a variety, it's kinetic, all your fibers should be the same, so shouldn't D be fixed for everything?
No,
Because otherwise this is gonna be higher dimensional if D is allowed to jump up, for example.
Well, what I'm saying, I'm sorry, what I mean is I fix a D and then I form this fiber bundle.
So really it should be like ED or something.
Yeah, like it's sort of parameterized by D, and then I can change D though.
So for every D, there is a fiber.
For every D, there is such a thing. Yeah, no, that's a good point. Yeah, for every D, there is such a thing. But for every D, we can form this thing called the embedding bundle. And then D is a parameter, right? It does not vary by fiber, it varies like totally. And then once you know that, let's call this thing by pi. This is what I happen to be calling it. This vector bundle can be pulled back along pi. Okay, then we get the pullback of the normal bundle, which I will abbreviate now just by N. That's okay. And then from there, the embedding bundle admits a sort of natural map into a Grassmannian, which I'll just call by G.
Yeah.
What is the map? Let me rewrite this a little bit lower. So what is the map here? The points of E approximately look like M comma in embedding, which I might call by phi. So how do you get a point of the Grossmannian from such a thing? You map it to, you know, like phi of, well, phi of the vector space, right? Phi of the vector space over M, which you might call by VM, well, right?
Right, so the image is a subspace and which corresponds with point of Grossmannian.
Yeah, so this is now affine Grossmannian, to be clear, right? Because it's like it's like subspaces of affine space.
Mhm.
But that's a morphism, right? That's defined everywhere. That's crucial. I'll explain why that's crucial in a moment, like when it's kind of interesting. And now with that, there's a universal bundle over G over the Grossmannian, right? There's a universal bundle over that. And then this can be realized as the pullback of that bundle. And so now we've set up this sort of diagram. In other words, given a resolution, we can form all of this other stuff. And you say, well, why would you want to do that? Well, now you have all these pairs. Right? So by this, I mean, you have U with its U is a bundle over G, and you can regard G as being inside of U, quote, by its zero section. Right? So now you have like a pair consisting of like U and quote U minus its zero section. With these bundles, these pairs. So there's that one, then you have another one. This one here. So that's another pair of interest. Then you have this one. And what's this? So this is N. There's N minus N. So again, I'm always regarding the base as like the zero section of this vector bundle. Right? This is a vector bundle. This is a vector bundle. This is a vector bundle. And now I have these more interesting pairs, which are not vector bundles. For example, M with Pn as a container. So you might call this by like Pn. Let me just call Pn by P from now on, please. P and P minus M. And then there is also orange. X and container Pn. Which again I'm calling by P. So P minus X. Yeah. So now we have all these pairs. And the pairs are related by a diagram, which we've set up. Right? So one more time, summarizing, we're saying if we have a resolution of the singularities of X in this sort of embedded way, right? This, which is very common to request, by the way. Like you don't just ask for M to X, you usually ask for an embedded resolution. That's usually what you do. Then you can make this diagram and you get all these pairs. And the pairs are related now in the following way. So if you take cohomology, however you want to, like whichever one you're thinking, right? Like let's not worry about what type or whatever, right? I mean, if it's singular, then great, you know, whatever. But then already you have pullback, right? So you can go this way. That's cool. And then you have this thing, and you say, do I have a map from the red to the yellow? It's like, well, I have a morphism this way, sure, but we usually pull back to cohomology, so that's not quite right. You know, so something is wrong, it's going the wrong way. But here's the thing. You see, this bundle, this is a vector bundle. Its fibers, you have to maybe take this on faith. If you happen to kind of know this, that's great. If you don't, I'll just tell you something and then you just have to kind of believe it. As D goes to infinity, right? So as D goes to infinity, which is something, again, that we have control over. We can push that however far we like. The fibers of fibers of quote red. Okay. Okay, maybe I'll not be so. It's okay. The fibers of red become. Oh, I'm sorry, not the fibers of red, the fibers of E to M. Sorry, what am I saying? The embedding bundle over M become arbitrarily contractible. Quote. So some people may be familiar with this sort of thing. Because there's like these, right? The idea is that the fibers of E to M are actually what are called like Stiefel manifolds or whatever, and Stiefel manifolds become more and more contractible as you increase the sort of embedding the sort of container space or the receptacle space. So what's the reason for bringing that up is if the fibers become arbitrarily contractible, then E essentially becomes M topologically. Right? E sort of becomes M. And so with that, you get like again, it's not obvious that you would have a map this way. And you kind of don't. But you have one quote up to homotopy. Where this is what I mean by up to homotopy.
Right, so involving the large D limit.
Yeah. So in the limit quote, you have a map. So that is a part that you should be a little skeptical of, right? And that's definitely like a bit weird, but let's say up to homotopy.
So in particular, big D means that when you want to make this whatever thing you're affine space you're embedding V in as big as high dimensional as needs be.
Yeah, as high dimensional as you need so that as many of these cohomology groups agree as you want.
Okay.
Right? Because you can make these fibers as contractible as you wish.
Can I ask a stupid question?
Yeah, it's fine.
Okay, good. A Nash equilibrium theorem says that everything can be embedded, if you go up enough dimensions. Why is that a role? Does that have a role here or something?
What's that?
Well, he wants it that nicely on the homology, so it does, that theorem right just says I can embed it, but that embedding might have not have nice properties that he wants on the homologies.
I guess what I'm trying to say here is this this map, if this were an isomorphism, then this would be an isomorphism, right? They just go bad. It's not an isomorphism because the fibers sort of obstruct that from being an isomorphism. But those fibers become, again, more and more contractible as I make D larger. And in particular, if I make D like, quote, 100, then the fibers will be contractible up to, say, homotopy group 100 or something. And then it's like, these will then be isomorphic on homotopy up to like the 100th degree. And then if I want to make it 1,000,000, I can do that. I just push this to 1,000,000, for example, and I just keep doing this at infinitum, quote. And then that's what this means, right? That D goes to infinity means the fibers of this become arbitrarily contractible. And then if you know that, then you get a section. And that section is exactly what we need so that we get a map this way, essentially. I guess I also want to point out, like, if people are getting kind of lost, let me step back for a second and just kind of relate this to something that we know. So we learn in topology that every vector bundle pulls back from the universal bundle, right? This is like a thing that we all learn. And then, but everybody always has to put in the caveat up to homotopy, right? So it's up to homotopy, is there such a thing? Why is it up to homotopy? This is the proof. This is literally the proof. So Dennis told me that this was sort of communicated to him, by Steenrod in some sense, and then this was shared later with other people, like this is the actual argument for why this is the case, right? It's up to homotopy because you only have this section up to increasing the fibers with this embedding dimension at infinitum. Okay, so so then with that, if you'll allow me, I'll say that I have a map up to homology. Okay, so I have a map. I have another map. Now n and n minus m, or the sort of relative cohomology of n to n minus m, is as long as we have a sort of tubular neighborhood theorem, which in singular cohomology exists, you're good to go, because then the homology of P relative to P minus M is going to be isomorphic, in fact, to this. So this is a little tough. Okay. Right. You have a map. So now you have a map and a map and a map. So we're almost there, right? And now you need a map to here somehow. Okay, so this one's tough because, right, like, you know, I don't see any obvious way that I can take the cohomology, right, of this to this. Now you can take the homology of M to the homology of X, right? The homology of M pushes forward to the homology of X. That's good news. If only we could relate the homology of M to the homology of this. Can we do that? Yes, right? That's duality. So by duality, this is related to this. This is isomorphic to this, in fact. Right? I don't know what to do now.
Yeah.
If I'll just do this, right? So each lower star now of M, right? By duality. And then this thing, this one's a little funky because this is not a manifold, so you might complain. But you do have it actually, because you have like sort of Lefschetz duality, at least in singular cohomology.
You have whose cohomology or whose duality?
Lefschetz.
Oh, Lefschetz.
Yeah, Lefschetz duality, yeah, or Alexander Lefschetz duality. So there is something you can do, at least in singular cohomology. Now, what you should be thinking about while I do all this is like, how is this going to work in positive characteristics? Right? Like, what are you talking about? It's like, yeah. So, okay, but anyway, you have a map now, right? Okay, so now, what's the punchline? We have all these maps, so we set up all these maps. There are these things called Steenrod operations that act on the cohomology of a space, basically, just in general. It's just a general principle that you have these things. So they act on this, right? And they act on this, and they act on this, and they act on this, and they act on this. And so I can take a Steenrod operation and by functoriality, port it to here, and port it to here, and port it to here, and port it to here. And in particular, in here, I have this thing, the dual of the fundamental class of X. And here I've got the dual of the fundamental class of the Grossmanian inside of this thing. This has to map to this by these maps. In particular, any Steenrod operation acting on this thing must act by sort of functoriality in this thing. In particular, if a Steenrod operation vanishes on this, in other words, if it acts trivially on this, it must act trivially on this. There are obstructions. They're all there. We just defined them, at least in this, nice setting where these sort of axioms hold.
So you're saying that if this works, I should be able to take in, make sure I better have every Steenrod operation of my Grossmanian work on my X.
Exactly. Any vanishing here has to vanish here.
Right.
These are obstructions. If we have a resolution, then any Steenrod operation that vanishes here, and these are usually well understood by topologists, must vanish on this thing.
Okay.
This is the goal. It says now I've set up this sort of storage, right? And now the point of the talk was to talk about the simplicial set, yeah. So this is not, in general, a topological diagram. This is just like a bunch of varieties In fact, this diagram is entirely in the category of algebraic varieties.
Yeah.
This works over a field of positive characteristics. Nothing I've said requires anything about characteristic zero, except for some of the axioms that I'm hoping for, like a tubular neighborhood and things like that.
Yeah.
But
Right.
the diagram exists.
So I guess where M is gonna now instead of being manifold, be one of the nice regular guys.
Still have a normal bundle.
Yeah.
Because I have a normal.
Yeah, I can take derivatives of
I
polynomials.
still have normal sheaf, and that gives rise to a total space, and then I can still make this thing. I still have a universal bundle over a Grassmannian. These are all varieties.
Mhm.
Everything is a variety. It's defined over, whatever, F2.
Mhm.
The thing is, yeah, there are these facts that I'm sort of using after the fact, which is like,
Well, the H,
is there H star? What does that even mean?
yeah.
Is there, are there Steenrod operations, right? Is there a tubular neighborhood theorem? That would be really nice, right? Stuff like that. Is there Lefschetz duality, right? These are all sort of axioms that you would want. So the first thing I want to just pause and say, like, okay, first, like, do we have any questions? Do we understand like the kind of roadmap? Yeah, I'll wait for a second. Maybe there's online questions. I don't know.
It was an online question,
Oh, it's sort
but,
of
but you're right.
Yeah.
Huh?
Chat.
No, I'm sorry. I thought you looked at it and said, sorry. Ready? Is the dimension D of the affine space inside the embedded bundle fixed or allowed to vary? And then you answered that, so you said thanks. And then it says, can you please explain again the map from the embedded bundle to the Grassmannian?
okay. So that one, sorry, whoever asked that was probably a while ago. So, so for each point of the embedding bundle, if this person still listens.
Who got? He got.
He got version.
Right.
Yeah. So he got, if you're still listening,
He's still on.
the point of the embedding bundle is a point M, and then an embedding over it, essentially. Right? Or it's really the set of all embeddings, but a point is like M and then one of the embeddings in that set. So you have to figure out how to send that to an element of the Grassmannian. So the natural thing to do is just to take the vector space over M and embed it into affine space. That gives you V as a subspace, or realizes V as a subspace of AD. And so if you want, this Grassmannian is maybe a little bit more explicitly described as VR of, well, the dimension of the normal bundle, which here is basically the dimension of Pn minus the dimension of M, which maybe I'll just call by like little b in capital B. Cool. Right. Okay, cool.
He
Yeah,
says
so-
thanks.
Great, yeah, no problem. Okay, so yeah, so we have this diagram. It's kind of insane looking right now. Yeah, and so
Right, so you say the issue is, yeah, the diagram makes sense, it's just how the heck do you do all the algebraic topology with it?
exactly, what is homology or cohomology? What is relative cohomology? Do you have normal bundle? I mean, do you have a tubular neighborhood theorem, stuff like this? So suppose you could take this whole diagram and apply a functor and turn everything into a space in such a way that it kind of agreed with usual topology, quote. Well, you can do that actually in some settings, right? In the complex case, there is a way to do that. There's the analytification functor. You can take all the complex varieties and regard them as analytic spaces, regular topological spaces, and then you do have, in fact, all this stuff. Right. So this is, the obstruction theory for the complex case, for example, or characteristic zero setting. Now, if the characteristic, well, you also have in positive characteristic, there is such a thing. It's called the étale homotopy type. which I will not get into. That's not really the point. But there is a way to prescribe a homotopy type in some sense, really a pro-homotopy type or whatever. Technically, to everything in this diagram that plays very well with something called analytic homology, which has relations to singular cohomology. For example, agrees with singular cohomology in certain cases. Okay, so that would be great. And that, taking it sort of back full circle, this is what Dennis proposed in 2004. Essentially, he did not show this, but he said, okay, there should be a way to, use the étale homotopy theory that he worked on back in like 1971 or so, or 1970, is these notes about how to use étale theory to attack the Adams conjecture. Right? So that's where that stems.
Okay.
And then they say, oh, well, why can't I use that to do this? Right? And so it seems like, it's very tempting. It's like, oh yeah, that should be possible. But the problem is there are these pesky things. There's this pesky person called Johann de Jong who proved that actually every variety, I mean, there's some extensions of de Jong's work actually beyond. I'll try not to erase things if I can avoid it. He showed that actually every time you want to solve this problem, you can almost solve it, regardless of the characteristic of the base field, in the sense that you can always arrange that you have m to x of degree a power of the characteristic. So like p to the n in some sense, right?
So the condition is if it's a resolution, you can do that?
Well,
Or any map
he
or
basically gives you what is otherwise a resolution, except for the fact that it's not birational. It's not an isomorphism on an
Yeah,
open
okay, so
subset. It's like a cover quote
okay,
on an open subset.
yeah, fine.
I mean, like I'm not going to get into the.
Yeah, that's fine. So, but the point is this map, I see. So this map is,
So it's called
right, like, right. Okay, it's not birational. Like you can fix that up. You can get that degree of power of the characteristic.
Exactly. Yeah. So you can get something that's like a cover essentially. It's
Okay.
like a good cover in certain places.
Mhm.
So that's pretty good. So I'm trying to kind of separate that. This is like new information. Sorry. I just don't want to erase things. I don't like erasing things because people get confused. So so it turns out that if you use étale homotopy theory, this alteration, the existence of this alteration, makes it so that all of the obstructions for the étale homotopy type already vanish. And you say, why? Well, because without getting into terrible technical detail, sorry, I'll try not to move, I'll just speak. So I'll just talk. So when the Steenrod operation acts, it essentially ends up multiplying the fundamental class by this power of the characteristic. But if we're working with coefficients that are prime to the characteristic, which is what you do in étale theory, then basically that multiplier will not be there. It'll be invertible. And then you will in fact solve Steenrod's problem on the nodes. There will be no multiple actually, because it'll be invertible and the characteristic is prime to the degree. If that makes sense. This is like super fast, but I just want to give the impression that alterations make it so that étale theory doesn't. Well, I mean, you can set up the obstructions for étale theory. You're welcome to do it. It's fine, but they will immediately. That all those obstructions vanish because the degree is going to be relatively prime to the characteristic in that setting. And so,
all the other theorems that you need here work in
Yeah,
étale.
yeah,
Tubular.
it all goes through. Yeah. I mean, Dennis's other student, Tobias Shin, had made a lot of inroads on setting that obstruction theory up. Actually, unfortunately, nothing is yet like really published or anything. But Tony Anala is a collaborator of his, that is still sort of actively working on things related to this. And I believe he would say that this is done. Like this obstruction theory is done.
For adult.
Yeah, it's created, it's constructed, and it doesn't get anything interesting really because everything vanished. So then you say, well, what to do? I don't know any other way to prescribe a homotopy type to an algebraic variety. Because it's over in F2, maybe there's something ridiculous, right? There's a bunch of points. So that is what this is about. It's building a simplicial set for every variety regardless of characteristic.
One thing,
Yeah.
we could also maybe use this board if you don't, since you don't like your race.
Am I welcome?
Yeah. I mean, we can just shift this right here, so.
Okay, that's great. Yeah.
Bring this thing right over.
So I will try.
There we go, perfect.
Yeah, I think I will be able to say now what this construction is, which is pretty
Yeah.
cool.
There we go.
Maybe I can.
No, look on the screen, if you do it on here, stuff there.
Oh.
Well, you can see on the TV if if you're an obstruction or not.
He's the Steenrod operations actually hilarious.
Oh, no. Now
Right, so what is this? So what to do? So basically what I'm saying is alterations, let me just summarize what I just said. Alterations, so this is really kind of like beyond. And then later, Offer Gabber they kind of put a bunch of stuff together and they showed whatever obstruction theory built quote via étale theory, which includes like the étale homotopy type and cohomology, already vanishes. Really useful, or yeah, whatever obstruction theory already vanished. Okay, so what to do? You could try to use étale homotopy theory and cohomology at the characteristic. I don't recommend it. It's pretty bad. In particular, H1 of the affine line with coefficients at the characteristic, quote, is absolutely horrific. It's certainly not trivial. And so it kind of ruins a whole bunch of parts of this argument, actually, because we need these fibers to be contractible, remember? Or these fibers will not be contractible. That'll be absolutely horrible. The contractibility of the fibers argument is going to break down because of this. Failed like miserably. So you don't want to do that. Let's say it's in call, what I mean here. So then, so like this is back in like 2000, 2001 or so. I mean, 2020, 2021 or so. This sort of came up because this other student was working on this problem, and I was like, I had sort of just recently joined the discussion in some sense, and I was like, well, yeah, of course not. Étale theory isn't going to work because blah blah blah. You know this thing, and then it was like, well, what are we going to do? And so I was like, well, why don't we think about motivic cohomology, which is sort of famous for being like topology. In other words, you would expect that this would be trivial in that setting, or at least it would be that the affine line should be regarded as sort of tractable. In other words, there's this whole sort of universe of results that people have probably heard of. I'm not claiming to know very much about it, but there's like A1 homotopy theory, which is sort of now pretty well known and well established, and it sort of purports to have contractibility of the affine line. That's what it says, right?
So this is Voivodsky's thing, or?
Yeah, exactly.
Okay.
Yeah, Morel and Voivodsky, etc. So A1 is contractible. That sounds promising. But that means you have to grapple with this thing that everybody's terrified of. right? Motivic homology.
So the question, are you more terrified of motivic homology or the Étale group of A1?
I think I'm more terrified of that, honestly, because this has to do with algebraic cycles, which are kind of like, okay, I think I kind of get that somewhat. At least I know what they are. So let me try to describe what is called the Bloch material. Okay, let's see how much time I have. Okay, like 15 minutes. Okay. So yeah, so the Bloch material of a variety, let's say F, is a simplicial set. Well, it's sort of like a bi-graded thing, in some sense. Yeah, I'm not exactly sure how to describe this. I'll just call it like a simplicial object. Let's say we take the Bloch material of dimension. This is Bloch with an H, by the way. Sorry, that's not clear. There's a lower subscript D, which is for dimension, and an upper subscript C, which is for codimension. I'll explain. You take the Bloch material of some, say, X, and it is the set of subvarieties Z, say. I have to be a little bit careful here. It's like these are closed. I would also like for them to be reduced, if people know what that means. If you don't know what it means, it just means when you look at the equations describing it, there's no nilpotence in some sense.
Who's Z again?
So Z is going to be a subvariety of something that I'm about to say.
Okay.
Yeah. I might as well say what it is, a subvariety first. It's not quite a subvariety. I'm trying to be a little bit more general. It's like almost like a subvariety.
Always.
Okay. Of X cross the simplex of dimension D. You say, what do you mean the simplex? We don't have the simplex. Yes, we do. We have the spectrum of whatever ground field you're using, the join variables up to the D dimension, and then subject to the obvious relation.
Right. So if we don't know what inequality is, we just ignore it.
Exactly, we just ignore it. So we have an algebraic simplex, right? We have this. And up to homotopy, it's just like what you know in the real numbers case. Same thing. Right? It just extends infinitely, cool. Okay, so you take closed, reduced. Let's see, what else do I want to know? I don't want irreducible necessarily. That's all I want. Let me just make sure I'm not missing any. Oh, and of course the codimension has to be C. The C. That's why I want that. Codimension C. Okay, so I have a codimension C that's fixed. I take all the closed, reduced codimension C subschemes, quote, of this stuff.
Oh, so Bloch material is a set of all Z's that do this.
Yeah, it's like
Yeah,
set of
set of
all
all.
these
Okay.
with a property, which I'm about
Yes.
to say. So the property is, let's make sure I get this right. Sure. So such that when I intersect, oh, excuse me. I'd like to do this for P actually, because I want to suggest that it's going to be a relative construction eventually. P, remember, is the ambient thing, right? So I can do this in general. And then try to relativize it. Z intersect P, well, cross both the face for any particular face. I'll say what a face is, but you can kind of guess what it is transverse. In other words, all quote intersections with the faces in the sort of appropriate way are transverse. So it's not just any closed subschemes, like any closed reduced subscheme of the coefficient, it's special ones with this property. Okay. And you can ask me what, well, face, I mean, I hope this is okay, what face means. It's just like what you get when you set one of these equal to 0, right? I'm not gonna say that explicitly, if that's okay. Transverse, you can complain, like, what does transverse mean? You know, you're working in an algebraic setting, I mean, you're blah, blah, blah. We have a definition, you know, thanks to Sayre, of intersection multiplicity in general, regardless of what you're doing, like for schemes, and I'm just asking that that intersection multiplicity is 1. That's all I'm asking, right? So that's a well-defined notion for these things. Yeah, so now we have this sort of bi-graded thing, right? It's graded by the codimension and the dimension. Okay, and in particular, I can fix one of these like C, and then I get a bunch of D's, a bunch of D sets, and I claim that there are maps between them, which I'm about to describe. Okay, and that will give us this simplicial structure that we want. Okay, because remember, a simplicial set is basically a bunch of sets that are graded, and then we have maps, right, to get.
It's only simplicial on D. So for every C, you're getting a simplicial.
That's correct, yeah. So for each C, I claim we're gonna get a simplicial thing, right? That's the idea. Okay. So, so just give me a moment, excuse me. Well, let me just describe this now. Without thinking about anything like that. So how does this, oh, question? No. Oh, I heard a breath, okay. So, yeah, so how do I take one of these things and get it to, so yeah, so fix C. Is this still visible?
Yeah.
Yeah, the whole board is in there.
Excellent. So fix a codimension C. Okay. Then we have well, block material with fixed codimension C, dimension D, like simplicial dimension D, and I want a map that will take me from this to here. So again, the codimension is fixed, and the dimension is what I would like to drop. So how would you do that? Think about it. You have this thing Z. It lives in P cross delta V. How are you going to make something that lives in P cross delta V minus 1?
Intersect with a face.
Intersect with the face, exactly. Now you see why I want transverse. Because if I don't ask for transverse, I will not know that I get something reduced after doing this in general. I'll explain, I'll show a little drawing. Okay, so what's the map? The map is D. D goes to Z. Intersect, well, Z sort of, well, cross. I guess I just want to do like Z intersect or
P cross.
E cross face, right, like this. That was in here. Yeah, okay.
Wait, sorry, in the beginning, do you fix the face with respect to which you're doing this, or?
I do not, and so you're right, and I'm about to say this, there are many maps, of course. These are the face maps.
Yeah.
So these are the so-called face maps that you would expect.
The definition you want the expression to be dispersed with respect to every face, not just.
Exactly, excuse me, for all faces, yes, right, for all faces, yes. Yeah, so for all faces, this is true. Now, why do I want this? I mean, let me just draw a little cartoon for the sake of drawing. So you have something in the algebraic simplex. Okay, let's say it looks like this. Uh-oh.
Yeah, that
Okay.
double point.
I intersect. Oh no, right? Then I get this thing. That's not reduced. Too bad. That's all I'm really worried about. That's very basic. That's true, because I just don't want that to happen. Okay, that's what I'm trying to rule out. Okay, so with that, for each C, we've got a simplicial set. I think it's pretty clear that this is a simplicial set. I would love to know if anybody has any objections to this. I mean, Emilio, we talked about this. I mean, I think it's true. Yeah, I mean, it has to be true.
It's gonna be.
It's a simplicial set. I'm pretty sure. I mean, at least up to homotopy.
I mean, you didn't say what the degeneracy were.
Yeah.
Semi-simplicial.
It's just a semi-simplicial set, and then it extends sort of, naturally.
Really.
Yeah, freely, quote. So I mean, I think it's okay.
But at least it's semi-simplicial, the maps compose
Yeah,
like they should.
yeah, it's good. So then with that, you can take its homology. Right? What does that mean? Well, at every level, you take this set and you form its abelian group. Right? The abelian group generated by that thing. But then when you do that, what do you get? Well, I called it the Bloch material, right? So you get Bloch's higher Chow groups. So the abelianization yields, well, excuse me, the abelianization of Bloch material, quote, C, and then simplicial grade is, well, gives Bloch higher Chow groups. Well, let me just say Bloch's complex that computes the higher Chow groups, if that's okay. Because I'm not literally saying they're the same. It gives the complex that computes the higher Chow groups. Which are, in the case of a smooth variety, the motivic cohomology. That's good. It recovers the motivic cohomology in the smooth case or the regular case, whatever we call it. Now, I'll say, well, if you've got this thing and its abelianization gives the higher Chow groups, which is the motivic cohomology, it's fairly well known. Excuse me, I'm not going to say like the technical details underlying this, but it's fairly well known that the motivic cohomology relates to the étale cohomology when the characteristic is not, excuse me, when the coefficients do not have characteristic divisible by the characteristic of the base field, for example, complex numbers. And so you will recover the étale cohomology, which then recovers the singular cohomology. And so it's reassuring that this construction recovers the singular cohomology of the complex variety. But it is a homotopy type. It's not just a cohomology. Yeah, and so I have to think.
Well, in fact, it's a family of them indexed by a C.
Exactly, it's a family of such things. That's even better. And so I have to thank Dennis for being so like, because I wanted to take cohomology because that's all I know. And he was like, no, you're not allowed to take cohomology. And then I was like, okay, fine, what am I gonna do? And then eventually we sort of together we're like, okay, well, how do you just go backward from Bloch's instruction and get something that's a homotopy type? Well, this is what we do. But I think that's all I have to say.
Well, so I guess the question is,
Well, let's take the speaker.
left hanging with the operations in that big diagram. Does this help?
These operations are not things that I understand even.
Okay,
These are built by topologists for topologists.
right.
Serious topologists know what these things are, and I'm not a serious topologist.
Meaning that, does this look like it's gonna,
Oh, there are Steenrod operations.
that's what so
Oh, yeah.
you can do that. That's what I meant to bring back that big diagram that.
There are Steenrod operations acting on, in fact, the sheaf cohomology for any cohomology theory.
Okay,
Any cohomology theory that is a sheaf cohomology theory has Steenrod operations.
okay.
Yes.
Right. Now, I know you said you need Steenrod operation, you need something like a tubular theorem or analog of it to make your thing
Yeah,
go through.
motivic cohomology and such a thing.
Okay,
I think, the game is to write this up, but for now I've been focusing on my project with Andrew Obis,
okay,
which is also like now in need of writing up, but is done.
okay.
So this is everything. But yeah, so I'm happy to take questions if people have questions.
Any questions from no questions from the internet? If you were to give part 2, what would it be?
I don't know. I was worried about having to give a part 1 or a part 2 or something, but I think I said what I wanted to say. So
No part 2.
yeah, I think this is good. Yeah,
I think it's excellent.
I can be happy.
Yeah.
Okay.
Anyways, let's thank the speaker again. Oops.
It's an online tour.
Yeah, it's an online. Anyways, but we're meeting here next week. So even if it's an online talk.
Yeah, no, thanks again, Nelson, for
Oh,
inviting.
please,
And Emilio, yeah, thanks for looping me in, yeah.
Christoph.
He's very active on Discord. On like the number theory Discord. Yeah. Yes. Good.
I think we're good. Anyways, ladies and gentlemen, so next week we will meet here again. What's the topic of it says? Oh, I'm sorry.
Geometric introduction to local language correspondence.
Geometric introduction to local language correspondence. Anyways, ladies and gentlemen, thank you very much. Have a wonderful